some quick notes from sections 4.2 through 4.4, actually. Whoops. This is 4.2 through 4.4. Got a little overzealous when I was doing the notes here. Okay, first off, you're going to see a lot of this summation notation. This is a capital sigma, all right, and it means add them all together. We have an index. You see this is a sub I. This is subscript, where the value of I runs from whatever number is right here. I'm starting at 1, and it goes to this number, n. So I've got n numbers being added together. That's what this means. So you plug in the 1 for your subscript, then you go to the 2, then you go to the 3, 4, 5 until you get to the top, okay? So this is just basic summation notation. You should have seen it in pre-calc 2. An infinite sum is where this n is infinity. Later on in calculus 2 and in differential equations, you'll go ahead and put the infinity up there. But for now in this book, we take the summation notation and we take the limit as that top value goes infinitely large. All right, what this is used for is to find the area between some function f of x and the x-axis. Now what happens is you take this area between the curve and the x-axis, they say under. You split it up into rectangles. This right here isn't an A, that's a C sub I. Hold the phone here, let me make that easier to read if I can. That's the letter C with a subscript I. So your index down there. So C sub I is somewhere in between A and B. All of your C's are between A and B. All right. Let's scroll back out. So we have this interval from A to B, and all of the x values in here are represented by the C's. That would be a C sub I in here, okay? In each interval, they're taking some x of it in between the two endpoints, the x, the last x and the current x, right? The subscript goes up, so I minus 1 to I, where the width of this rectangle is called delta x, and that's just the distance between the two x values at the sides. The height of that rectangle will be that value c, which is somewhere in the middle, plugged into the function. That gives me the height of the rectangle, the width is the delta x, and if we multiply height times width, we get area. So the area of this rectangle is the f of x here, choosing an x, and it runs from 1 to n, and we're taking each of those x values in there, plugging it into the function to get the height of the rectangle, times the width of every rectangle. And what we need to understand for now is that the area between the curve and the x-axis is this infinite sum, but the very definition of an integral, a definite integral here, is this infinite sum. So we've learned how to do some integration. Next, we're going to learn how to do a definite integral that has these limits on it to find the area between the curve and the x-axis, among other things. Okay, so notice that I put under in quotation marks here. The area under the curve is understood to be the area between the curve and the x-axis. Now, when the curve is above the x-axis, this area will be positive. If the curve is below the x-axis, this area will be negative. So if you're finding the absolute value of the area, you're going to have to stop integrating when you get right here, and you're going to have to make two separate integrals because this area is a different sign than this area. So you'll have to stop here and then start again and integrate and make this area negative so that you're actually adding it. There's more, you'll learn how to do that in Calc 2. But there's more to it than that, because sometimes you need this part to be negative to combine with this positive to get the net value. Okay, so when we have the integral of our function with our differential here, but we have limits, these are x values, and they're called the limits of integration, and we're finding a definite integral. Now, all of the integrals that we've done so far, we didn't have limits. Those were indefinite integrals, and we always got plus c at the end. You'll see in my demonstration later that the plus c is going to go away when we have limits on our integration. Okay, so remember, if f of x is positive, then this definite integral is the actual total area between the curve and the x-axis from x equals a to x equals b. All right? But if sum of f of x is above the x-axis, positive values of y, and sum of it is below negative values of y, then if we integrate just from a to b, the negative area subtracts away from the positive, and we get what's called the net value of that. Okay? Now, a lot of times it's necessary to find the net instead of finding the absolute value of all of the areas. For instance, let's say this f of x right here represented the profits in your company. Well, the positive profits will be actual profits, whereas the negative will be losses. And you don't want to make the losses positive and add them to the profits unless you are cooking your books or cheating or something like that, okay? Because you want your losses to subtract from your profits, because the net value is what you're actually looking for. So how do you evaluate a definite integral? First, you got to integrate it the same way you always did. But then we have to evaluate at our limits. So to evaluate at the limits, you're going to plug in the top number, then you're going to plug in the bottom number, and then you're going to subtract. You always subtract, and it's always top minus bottom. It is always that way. Got it? So, for example, we're integrating this polynomial on the interval from 1 to 4. These are x values, all right? So we're integrating with respect to x. I'm going to get add 1 to the power, divide by the power. That gives me x to the 3, and that 3 divides away. I'm going to get x to the 2, and divide away the 2. I get 2 divided by 2 is 2. 4 divided by 2 is 2, right? And this is just 7x. So here's my integral. And notice that plus c, that integral of, that constant of integration. But now I'm going to evaluate it. So I'm going to take this top number 4, and I'm going to plug it in for each of the x values. That gives me this. Then I'm going to take the bottom number, the 1, and I'm going to plug it in for each of these x values. That gives me this. And when I have that, notice that I've got a big fat minus sign in the middle, which gets distributed to each of these pieces. In other words, that minus is going to get that in front of that c. I'll have a plus c and a minus c. So when you're doing a definite integral, the plus c always subtracts away, because it's not multiplied by an x, so it doesn't have, the limits don't have any effect on it, and it's always the front c minus the back c. They always go away. So you evaluate this. That's a 64. This is a 16 times negative 2 gives me this. That's minus 28. Be really careful with your minus signs, especially if you're plugging in a negative number, because if you have a negative number cubed and then squared and then all of the subtraction in here, and then it's the top minus the bottom, You got a whole lot of minus signs in there, so you got to really watch it. All right, I'm going to evaluate here. I get a 4. Evaluate in here, I get -8. Don't forget you're subtracting that negative. So it's adding, and my total value of this definite integral is a 12. All of the homework that you're going to be doing is definite integrals. So that's all you have to do. First, you integrate the function, then you plug in the top number, plug in the bottom number, big fat minus in the middle, you're going to get a number at the end. Next, if I'm integrating the sign, I have to ask myself, what is this the derivative of? Well, negative sign is the derivative of cosine. So when I undo the integral, I get a minus cosine, and the coefficient just goes along for the ride. Integrate the cosine. Cosine is the derivative of sine. You just get plain old sine. And the 3 goes along for the ride. Now I've got to, this is an evaluated from 0 to pi over 4. I don't think I mentioned that last time. When you take the integral, you no longer have the integral symbol. You're going to have the evaluation bar at the end. The top is here, the bottom is here. Once you've integrated, you plug the top number in, the cosine of pi over 4, the sine of pi over 4 with their coefficients there. Then I'm going to plug in the 0, and I wrote that down because I bet you don't remember the cosine and the sine of 0. Cosine of 0 is 1, sine of 0 is 0. We love zeros, by the way. So this piece is just -5, and this piece is just a 0. So I've got -5 root 2 plus 3 root 2, both over 2, which gives me -2 root 2s over 2. These cancel. I get negative square root of 2 and a +5 because I subtracted the negative. Be careful with your minuses. Okay, that was 4.2 and 4.3. Now in 4.4, we get a bunch of theorems. The fundamental theorem of calculus says that if this thing is the derivative, in this case of capital F, I integrate, I get capital F, but I plug in the top number, and I plug in the bottom number, and I subtract, and that's it. This is the derivative. When you take the integral, you get the function. Plug in the top, plug in the bottom, subtract. There's your fundamental theorem of calculus. All right? Mean value theorem, very cool, because if you look at my picture here, say I've got some function. Well, the area under there, which is the integral from a to b of the function, is marked in the green, right? But there's some number, some x value in between a and b, where the y value, if I just make a rectangle here, and I find the area of that rectangle, see this little pink area is outside and this is outside, but that green is also outside, so it kind of subtracts. There is some x value in between these two endpoints where if I took the y value and I made that the height, and this whole width is the width, area of a rectangle is width times height, right? Well, the width here is b minus a. It's just the distance on the x-axis. And the height of that rectangle is the y value of some x value in between the a and b. So this is width times height, okay? This area is just going to be the width of the rectangle times the height of the rectangle. And this comes from the next theorem on the next page. So the mean value theorem just says that I can take the integral and evaluate it from a to b. There is some c in the middle, whereas if I take the entire width, I can find a c that will make the height be the average of the y values for that whole thing, so that this area of the rectangle is the same as the area under the curve. And what we just did comes from the average y value. Okay, when it says the average value, it means the average y. So if you look at that picture from the previous page, you'll see, remember, this is the area, right? This is the area, and it's width times height. If I just take this equation and divide away the width, then I get the total area divided by the width is going to equal the average y value on that interval. And C is in between A and B. So the average y value of that function on this interval would be the height of the rectangle, B minus A is the width, and there's the actual definite perfect area under the curve. So the two theorems work together. I know it's confusing, doesn't matter. So whatever. All right, the second fundamental theorem of calculus is that the derivative of the integral gives me the function. Now, two things to notice. The second thing, the derivative of the integral gives me the function because the integral is the antiderivative. So if you take the derivative of the antiderivative, they undo each other and you end up with just your function. But notice that this integral is with respect to t, and one of the limits is x. Okay? There are some processes where you're going to need to leave, instead of having the function, you're going to need to leave it as an integral while you're doing all the processes. Believe it or not, there's some integrals that just can't be done, but you can use this notation in the process of your work. And so we call t a dummy variable. We've taken f of x and replaced all of it with the t's, and we're going to integrate it with respect to that t, but then when we evaluate it, we're going to evaluate it with the top limit as x. Most of the time, the bottom limit doesn't matter because it's going to give you a constant. And remember, you always get a constant when you integrate. So some processes will dictate what this number is at the bottom. We will not be doing that in Calc 1. You'll be doing that later, and when the time comes, it will be explained. So this is the second fundamental theorem of calculus, and really what it's saying is that the derivative of the integral is just the function. So at this point, you should be able to complete all of the homework in 1.3 and 4.3 and 4.4. There is no assignment for 4.2, but you need to watch that extra video that I posted, which explains all of the stuff that's covered in 4.2 and 4.3. Then get on that homework so that you can practice taking definite integrals.